Hi, in this video we will be going over the SIMPLIS Magnetics Design Module, or MDM for short, which is a new add-on module for symmetric SIMPLIS starting from version 8.4. First, I would like to go through the motivation for developing MDM, and that is that electric and magnetic design in power converters is tightly coupled. So designing a converter, we will start with some converter design requirements, which will include the input voltage, the output power, and some efficiency and size targets. So this will determine the requirements of our electrical circuit, and that in turn will determine the requirements of our magnetics design, of any inductors or transformers that may be in the converter. The design of that magnetics influences the electrical performance of the converter, and of course the magnetics performance, but the performance of the entire circuit also influences the performance of the magnetics, for example, the losses in the magnetic components. And all of this goes back to affecting our design targets, such as efficiency and size. A good way to realize that is to look at the isolated LLC DC to DC converter, which contains a resonant inductor with an inductance L and a transformer with a turns ratio and a magnetizing inductance L mag. So these two parameters will of course affect our switching frequency in this converter, which will affect our switching loss, our output ripple, our capacitor loss, and of course also our magnetics loss. So we can pick L and L mag and design to spec, and of course the turns ratio as well. But until we really design the magnetics themselves, we do not know the equivalent series resistance of the inductor and the transformer, nor the leakage inductance of the transformer. And these two will affect the switching frequency and then the performance of the entire circuit as a result. And even small changes in these design parameters can affect our performance. So to illustrate this and to illustrate the use of MDM, we will be going in this video through a design example demo based on an Infineon app note for a 600 watt LLC eval board with 600 volt CMOS transistors. And I would like to thank Infineon and especially John Hancock for their help in setting up this example. This is the 600 watt LLC converter eval board that we will be modeling in SIMPLIS. It has a nominal input voltage of 380 volt DC, output voltage 12 volt DC at 50 amps full load, and these are the two components that we will be modeling using the magnetics design module, the RM core resonant inductor, and the PQ core transformer right beside it. So now I would like to go into the circuit. This is our schematic in SIMPLIS. It fully models the eval board I just showed you on that slide. The switches, the diodes, the compensation loop, all of that is modeled very accurately, and in this case also including the magnetic components. And we are set up to run this in closed loop at full load, 600 watts. So if I zoom in, we can now look at the magnetic components in more detail. So let's take a look at the resonant inductor first. The resonant inductor is a standard SIMPLIS symbol, the multi-level lossy PWL inductor that has been available for quite some time. But now there is an additional model level, level 2, where the magnetics design module can be used to define a physical model of the inductor. So at level 2, we have this button, Edit with SIMPLIS MDM, or Create with SIMPLIS MDM if no model has been created yet. And when we click this, it will bring up the magnetics design module main window. This main window consists of 3 tabs, the core tab, the winding tab, and the cooling tab. In the core tab, we select a core shape and a particular core from the MDM database, or we can define the core geometry for a particular shape manually. In this case, we are modeling the core that is used on the eval board. It's an RM12 core. And we pick a material. In this case, it's TDK N87. And then we gap the core by adjusting the air gap to get the desired inductance, which in this case was 14 microhenry. In the winding tab, we define how the wire is wound around the core. We define the bobbin parameters, and then we select a wire or define a wire geometry manually. And in this case, a Litz wire using 120 strands of AWG38 wire is what is used on the eval board, and that is what we are modeling here. Finally, we have the cooling tab. And in the cooling tab, we can, for example, just set a constant temperature. This means that no thermal calculations are performed. It's just assumed that the windings in the core are at this temperature. We can select force convection, where we define an ambient temperature and an airflow speed and the direction of airflow compared to the component. So we are modeling how the fan is blowing air at the component. Or what we're doing in this case, because that is the case on the eval board, we are doing a natural convection with an ambient temperature of 35 degrees. And once we have selected all of that, we can click Finish. And now the piecewise linear inductance calculated from that physical inductor model that we have defined in MDM is written back into the symbol here. A similar story is repeated with the transformer. Now, to facilitate the use of MDM, but not only the use of MDM, in 8.4 we have a new symbol called the Multilevel Lossy Transformer, and it's located in the part selector under Magnetics, Transformers, and here it is right here. So when you want to create a new one or you double click an existing one, there are 2 tabs. There is a winding tab where you define the number of primaries and secondaries and the number of turns. And there is a model parameters tab where we now have 4 model levels. Level 0 is just a standard T model with a constant magnetizing inductance. Level 1 turns that magnetizing inductance into a piecewise linear inductance. Level 2 adds a constant leakage reflected to the primary and a DC resistance for each winding. And level 3 is now the model created by the SIMPLIS magnetics design module. And this model is in fact a magnetic circuit, a reluctance circuit, which is simulated at the same time as the entire circuit schematic. So it's not just a T model. Level 0 to 2 can be used without SIMPLIS MDM, but for level 3 we need to use SIMPLIS MDM. So as with the inductor, we click on this button here to generate or view the MDM model. And now the main MDM window has come up again, but now it's configured for transformers. The core tab is pretty much the same. So we have again a core selection. In this case, it's a PQ35 core. And the material being used is PC95, also from TDK. The winding tab is now slightly different. The number of windings is fixed by the dialog for the multi-level lossy transformer that you saw earlier, but you can here adjust both the number of turns and the construction of each winding. So in this case, we have split the primary winding into 2. This is an interleave design. This is what is used on the demo board, and is also the secondary is also split into two. So these bifilar Litz windings that you see in blue and in purple are in fact the primary winding split into two, and the red and green foil winding is the two turns of the secondary winding split into two. For each winding, again, we can define a wire or a foil, as is the case with the secondary windings, where we can define the dimensions of the foil. And similarly, again, we have the cooling, which is the same as in the inductor case. So now, when I click Finish here, MDM has generated the magnetic circuit or reluctance circuit model and has written it back to this symbol here. And this will now be simulated when we simulate the entire converter schematic, and the fluxes inside each leg of the transformer will be calculated in the circuit simulation. So how do we use MDM to get a detailed breakdown of the performance of our magnetic component? This is done as a post-processing step. So first, the circuit simulation is run, and then the waveforms from the circuit simulation are passed on to MDM to calculate detailed losses in the inductor and transformer. In order to enable that, we must both place a power probe on these symbols, and inside the dialog for the inductor and the transformer, check this box to tell the power probe to initiate the MDM post-processing, and we must tell it the fundamental frequency of the waveform, as well as its shape. So in this case, we know that in the LLC converter, the wave shape for the flux inside the resonant inductor is a collection of sinusoidal harmonics, whereas we know that in the transformer, the flux is piecewise linear, it's triangular. With those two boxes checked, we now run the simulation. And now we have the results for the inductor, and the transformer will take a bit longer because it's a more complicated design, especially due to the foil windings. So MDM has generated two results windows, one for the inductor, the other for the transformer. You can see here the name of the symbol, so you know what it's referring to. And we see a breakdown of the losses by both winding and core, and also by type when we talk about winding losses, so whether there are DC losses, AC conduction losses, skin effect losses, or proximity effect losses. In this case, we do not have losses due to DC bias because the average current in both components is 0. Of course, we have AC conduction loss. This is the square of the RMS current times the resistance. And we have proximity effect losses in the inductor. So we can go more deeply into the results by clicking on the next tab, which is losses by winding. And here we can see the density of the loss by turn. And you can see that here in the inductor, these turns around the air gap are red, and this is the effect of the air gap fringing field, the air gap fringing flux causing extra proximity loss in the windings, and we see that proximity loss here in this breakdown. You can see in the transformer that there are not very many proximity losses, as our breakdown is telling us, and we can see that there is very little proximity loss in the Litz wire, and that there is some proximity loss here at the edges of the foil windings. But overall, the windings are pretty much all blue, and you can tell that this is a well-designed, well-optimized inductor, transformer, sorry. So now the question is, what happens if we change something? So we can go into the inductor and say, well, what if we put more copper in there and want to use a bifilar winding? So we can change the winding to a bifilar, but now we see that we need to use a slightly longer bobbin in order to accommodate all these turns in this core. So we can adjust the bobbin height, assuming such a bobbin exists. And now they can all fit. To move things along a bit quicker, I'm going to disable the post-processing on the transformer because we're just interested in the inductor here. And run the simulation again. Now, the first interesting thing you can see here is that our frequency has shifted ever so slightly. That is because by changing the design of the inductor, we have changed the ESR. So this is not a huge influence, but we can see that the frequency has changed by 0.1 kilohertz, the switching frequency of the circuit. Now we can compare these new results here with the previous ones. And we can see that by going to a bifilar winding, we have actually increased our loss. Core losses are about the same, but proximity losses are significantly higher. So if we look at the AC conduction loss, here it was 0.13 watts, here it's 0.068. So by doubling the amount of copper in the winding window, we have about halved the AC conduction loss, which is expected. But if we look at here the losses by winding for each of the two designs, we will see that now we have a lot more turns closer to the outer air gaps here as well, which means that that is now contributing to the proximity loss, and our proximity loss is going up. So we can illustrate also what happens when we change the transformer design. So for that, I have prepared a different schematic where the primary windings are not interleaved with the secondary. So if you zoom in, we can see here that there is only one primary winding. And if we look at the design, we will see that this is a completely different design compared to the previous one, which was following the Infineon eval board. So it's still a PC95 core, but this time it's a pot core, so it's a different geometry, not a PQ. And if we look at the wires, we don't have bifilar windings anymore for the primary. And instead of using foils for the two secondary windings, we are using a 5-filar solid round wire. And the cooling is the same as before. So also I'd like you to pay attention again to the switching frequency we had in the previous example, which was 132 kilohertz, and see what happens when we run this now. So first of all, now our switching frequency is 138 kilohertz. So that's a noticeable change from before, even though we have the same resonant inductance and the same magnetizing inductance. And now we can take a look why that is. So this is our old transformer with the interleaved windings. And this is our new transformer. So since we had interleaved windings in the first case, this Lmag should be multiplied by 4 to get the total magnetizing inductance, because we split the primary into 2 equal halves. So the magnetizing inductance looking from the primary side is actually the same, 44 versus 188. But we can see here that the leakage inductance is quite different. So our first design with the PQ core had a leakage inductance of 1.77 microhenry if we reflect that all to the primary, whereas our leakage inductance for the pot core design is 8 microhenry, and this is what is causing the difference in our switching frequency of the LFC converter. We can see that the pot core design has noticeably larger losses compared to the PQ design, that the windings are going to 114 degrees compared to 70 degrees for the PQ design. And we can see why that is when we look. If we look back, we see that we have a lot of proximity loss here, and we can see very clearly when we look at the losses by turn that the air gaps here are causing a considerable proximity loss, as this core has 3 air gaps where this one has 1, and just the general arrangement of the windings is causing more proximity loss. The MDM results window will also give the waveforms for the magnetic component. So in this case, for the transformer, we will see the flux in each leg of the transformer, the flux density, and of course the current and voltage in each winding. And then we will also see a plot of the magnetizing inductance versus the current. So you can see at which current it is saturating. And finally, there is a textual summary of the transformer design, and the same thing applies for inductors. So here you can see how the magnetics design module can help you design your magnetics components at the same time as you're designing your circuit, and really optimize both your circuit and your magnetics for performance and to meet your design targets. Thanks for watching. Goodbye.